Hi everybody, so this is Ms. Ward. This is our first section of notes going over the characteristics of chemical bonds. So this is the very first page of your note packet dealing with HAPPY. This note section is going to be broken up into two pieces. So this is for day 1, and then you'll have day 2's notes, day 3's notes, etc. Okay, so of the section 1, the objectives of this section are to learn about ionic and covalent bonds and explain how they're formed, to learn about what a polar covalent bond is, to understand the nature of bonds and how their relationships relate back to electronegativity, and to understand bond polarity and how it's related to molecular polarity. So those are all the things we should hopefully accomplish in section 1. So the first thing to talk about and to understand is that compounds make up almost every single thing around us. So basically, everything you touch, breathe, drink, deal with on a daily basis, almost all of it is made up of compounds. So even if you have a solid element, so a gold nugget, for example, those individual gold elements, those gold atoms, are bonded to the other gold atoms. If they weren't, it wouldn't be like the solid substance, okay? It would fall apart. So anything that's going to be solid is going to have some sort of bonding that's happening there. You can have substances that are composed of atoms not bonded, but it is very rare, even in gases. Many of the gases we deal with, hydrogen, oxygen, we know that those are diatomic. So hydrogen is bonded to another hydrogen, oxygen bonded to another oxygen. So even within gases, it's rare for them to not be bonded, but it can happen. One example is argon. Argon can exist does exist in the atmosphere as a gas and as a single individual atom. So you can have those individual atoms, it's just not very common. So the way things bond are always going to affect a thing's chemical substance and its physical properties. The way things bond, the type of bonds, the strength of the bonds, all of those things will determine a lot about what that substance is. Carbon is a perfect example of this. Most people know that carbon in its pure form, just carbon, exists in two general types. You've got graphite, which we know is soft, slippery, it's cheap. It's what they use for pencils. And then they also have diamond, which was one of the hardest materials known to man. It's extremely expensive. It's very rare. So both of those are 100% carbon, but the difference between them is how they're bonded. So they are not bonded in the same way, and so therefore they have completely different substances. So as we start talking about these chemical bonds, it's important that we understand what the definition of a chemical bond is. And that is, it's a force that holds groups of 2 or more atoms together and make them function as one piece. So if you look at water, for an example, H2O is made up of 2 bonds, one from the oxygen to the hydrogen, and another one from the same oxygen to the other hydrogen. So there's 2 OH bonds. When we draw bonds in chemistry, we use a straight line to represent a bond holding 2 atoms together. The strength of a bond is determined by measuring the bond's energy. So different types of bonds, different types of combinations of elements are going to have different bond energies. And when we say bond energy, we're talking about the amount of energy that's needed to break the bond. So if we're to measure how much energy we have to put into order to separate that hydrogen from the oxygen, that amount of energy is the bond energy. When we talk about breaking bonds, you can also talk about forming bonds. They're inverses in terms of what they're doing, the type of reaction. Breaking bonds absorb energy, making it, if something's absorbing energy, it's taking on that energy. That makes it an endothermic process. And forming bonds, putting those bonds together, is going to release energy out into its surroundings, its environment, making it an exothermic process. So breaking bonds absorbs energy, forming bonds, it releases energy. Okay, so as we talk about all these bonds, let's talk about the different types of bonds. So the first type of bonding that we have, we've talked about 2 different types of bonds throughout all of chemistry. We've talked about ionic and then molecular covalent bonds. But now we're going to be breaking up those covalent bonds. Instead of just talking about them in terms of ionic and covalent, we're now going to be talking about them in terms of whether something is ionic, what we call pure covalent, or something we call polar covalent. Okay, you may have heard the word polar before come into play with chemistry terms. This was where we really start getting involved in what that means. So the covalent bonds have 2 different types of bonding. All right, Ionic bonding is when we have a transfer of electrons. So one ion is giving its electrons to another ion. One atom loses electrons, one atom gains electrons, making their ions. We know that ionic bonds are formed between metals and nonmetals, and so when they mix together, we get some sort of positive ion and some sort of negative ion, those cations and those anions. Almost everything that we've dealt with up to this point in terms of forming, like when we do chemical reactions and things like that, almost all of them have been ionic compounds. The only times we've done things with covalent compounds, like you wouldn't predict a covalent compound. We always give you those sorts of answers. So most of what you've dealt with at this point have been dealing with ionic bonding. The next type of bonding we have is something called pure covalent. In a pure covalent bond, they equally share electrons. Overall, the difference between covalent and ionic, they're stealing electrons. In covalent bonds, they share electrons. But not all covalent bonds share electrons the same way. A pure covalent bond equally shares those electrons. So there is no sort of charge in any sense of the word. They completely share them. They are 100% equal. Everything is fair all the way down. You typically see this in circumstances with diatomics or noble gases. So, a hydrogen and a hydrogen are not going to, share electrons differently. They are equally sharing them amongst one another. So you'll see this complete equal pairing. The other type of covalent bonding we have are polar covalent bonding, and this is when you have an unequal sharing of electrons. So the atoms bonding together are similar, but they're not identical. So it's still going to be two nonmetals because that hasn't changed. Ionic is metal and a nonmetal. Covalent molecular is going to be two nonmetals. And the difference, though, is that one of the atoms that are bonding are going to have a higher electronegativity than the other. We'll be looking at some numbers, and there is some statistics as to what the difference between them has to be in order for this to happen. But in a situation like you see here, we have a hydrogen bonding to a fluorine. Okay. In this situation, the fluorine is much more electronegative than the hydrogen. So while they are still technically sharing electrons, the fluorine is being a bit of a hog about it. And it wants more of the electrons on its side than the hydrogen does. And the hydrogen doesn't care as much, so that's okay. So there's sort of a what we refer to as a dipole situation is what happens. So one ends up being slightly positively charged, one shows up slightly negatively charged. And we call that a dipole moment. So you can see here that there are symbols. This is the symbol for dipole. It's like kind of like a curvy S, so it goes like this, and it kind of comes into itself is what it looks like. And then this is the positive, and then this is the negative. So when it's a negative charge you see here, you see the positive here. These dots, this is literally showing you how these electrons, this is like a map of those electrons, showing you where they're most likely to be. So you might have some electrons in the hydrogen, but way more likely to find them in the fluorine. Whereas up here, you can notice that it was equal amongst both of them, that they're equally sharing those electrons. So atoms that have that partial charge are polar is what we refer to. So like North Pole, South Pole. So we've got positive and negative. So when things are polar, that means they have at least some slight charge to them on one side or the other, whether it's positive or negative. And that's due to that unequal sharing of electrons. All right, we got one more thing I'm going to show you guys, and then I will cut it off for today, and that is the electronegativity. So electronegativity is one of those trends that we did talk about last chapter, in chapter 11. So all of those periodic trends, we always think in our head, okay, is this going to increase towards fluorine or increase towards francium? And in this case, it does increase towards fluorine. All right, so it's increasing from left to right, and then from bottom to top, it gets biggest. So fluorine has the largest electronegativity, and francium has the lowest electronegativity. Electronegativity is the relative ability of an atom to attract shared electrons to itself. So this is how much it wants to gain those electrons. So the more it wants to gain those electrons, the higher its electronegativity, which is why fluorine has such a high electronegativity. All right, that's it for tonight's notes. Use this to help you with your homework. Have a good night.